Let's have a look at it, shall we? Now, they provide this substitution. Okay. I'll say right from the outset, they're a bit sneaky in the way that they do this. And the answers in particular, they lack a lot of detail, particularly with regard to restrictions. Okay. When they use this substitution and introduce it, they make a whole bunch of assumptions about the restrictions that they'd never resolve, really. But I want you to have a think about the way we set it up and what we finally end up with. I wonder if you can determine what the restrictions are. It's not that complicated, but you should address it. Okay. So they've started us off with this. And in order to make a substitution, obviously you'll need a derivative, right? So we're going to do dx on d theta. And that's going to give you, well, it's sine theta all squared, right? So you're just doing your normal chain rule, right? You can do the inside. The inside function is sine, so its derivative is cos. And then you do the outside. It's something squared. So the power comes out the front. And you reduce the power by 1. There you go. 2 sine theta cos theta. You might be tempted to put that into double angle formula because you can see that that's sine 2 theta. But you may be able to see that when you bring this back over here, it's not going to actually be any advantage to you to simplify it in that way and use that identity. Okay. Good. So we've got that in place. Do I need any other pieces in order to substitute this in? Looks okay to me. I think we can start going on this. So this is going to be equal to, and we'll do all of the substitution all at once. Okay. We're going to get the square root of sine squared on 1 minus sine squared. Okay. Now that dx here, that's going to be replaced by 2 sine theta cos theta d theta, right? Trailing off over here. Okay. And you can see, clearly we can do some cancelling here. But you have to be careful because of the restrictions and the cases that you need to introduce into here, right? So you got sine squared over there. Your denominator, of course, is going to be cos squared. So you've got the square root of sine squared on cos squared. You might be tempted to turn that into tan. But based on what I have over here, there's kind of not much point, is there? I'm going to write that as this. Okay. Now, this is kind of the line that the textbook goes through when it gets its answer. I know because of how it simplifies it out. But strictly speaking, this, the square root of sine squared on cos squared, is not exactly sine on cos, is it? What's the difference? What's been missed? There really should be an absolute value around these, shouldn't there? Because by definition, this thing, it has to be positive, right? Because it's a square root, yeah? So really there should be this at the front. The answer doesn't address that though, as you'll see why it's just going to simplify out. I just want you to be mindful of the fact that when you evaluate the square root of a square number, you're always going to get something positive, hence absolute value. Regardless, what happens here? You can see that the causes are going to cancel, right? So what are we going to get? You're going to get the integral of 2 sine squared. Okay. Now, suggestions? What can we do with this then? You've met this before. You've met it in 3 unit, haven't you? What can we do? Now double angle, right? So 2 sine squared theta, you want to get this in terms of cos 2 theta. Just over on the side, you might note down, cos 2 theta, we're going to use the 1 minus 2 sine squared theta form of the identity, right? That's kind of convenient that it's already a 2 there. These guys just need to swap places, don't they? 2 sine squared is 1 minus cos 2 theta. Okay? So therefore, I can put that back into here. Okay? And I'm kind of done, right? I can deal with this. What's the 1 going to turn into? Just theta. Okay. What's the cos 2 theta going to turn into? Minus half sine 2 theta. Does that check out? You can check, you can integrate it back. Sorry, differentiate it back. And you should end up with cos 2 theta because that 2.5 cancel. All good. Okay. So now I've resolved my integral, but I'm not done yet. Why not? it's all in thetas, right? Which are foreign to the question. We introduced the thetas in order to get it into a form that was easier to work with. But now we've got to get rid of them, okay? So you have some problems. You got x equals sine squared theta. That was the substitution they introduced, okay? I don't have either of those here, okay? So what I need to do is I need to twist and turn this thing in order to get these pieces out, right? So for example, if you wanted theta, what would you do? If I want theta on its own out of this. Well, for starters, this thing's squared, right? So I don't want squares. I'm going to need to take the square root of both sides, okay? Now the textbook does this. It just assumes that, but of course you can't really, can you? Because what is it really equal to? It's equal to plus minus, right? So you see what I mean? The textbook just gives you the answer, and the indefinite integral, it's one of the primitives, but it doesn't account for all of the cases, right? So they just deal with this, and they say, therefore, theta is equal to sine inverse, which again, if you've taken sine inverse of both sides, again introduces another restriction, right? Gotta be super careful. So I can at least put that into there. That's good. I haven't dealt with the sine 2 theta though. What do I do with that? Now we saw the sine 2 theta here, so we're like, well, that's dx on d theta, but that's no help. That's still got thetas in it, okay? So what kinds of options do we have? Well, I know what sine theta is, right? And there's a sine theta hiding in the sine 2 theta, right? What identity can I use here to help me? This is double angle, right? So I've got the theta still there. This part here is 2 sine theta cos theta. So the 2.5, that's just this, isn't it? Okay, is this better or worse? It is a bit better, because at least I know what sine is, right? So I can deal with that, but I don't know what cos is. Do I? If we know sine, we know cos, okay? Because cos is defined off of sine. So there's a couple of different ways to go about this. Probably the most direct way is to come back to this guy, right? This tells you, based on the fact that now I'm only considering this within a certain domain, right? A very, very restricted domain. I can draw a triangle off of this, right-angled triangle, like so, okay? If I put theta over here, what does this ratio tell me about any of the sides? What can I put on there? Sine is opposite on hypotenuse, isn't it? Opposite on hypotenuse, that's root x, and that's 1, okay? So that would make this side down here, by Pythagoras, the square root of 1 minus x? Is that right? Yeah, because you square these both, and you add them together, you get the hypotenuse. Good. So therefore, out of this, I get that cos theta is adjacent on hypotenuse, which is the square root of 1 minus x. There you go. If you know sine, you can get cos out, supposing you're within a restricted domain. Okay. So now I've got all my pieces. Sine inverse of root x, just taking that positive case, minus, now there's sine theta and there's cos theta, they're both square roots, aren't they? So I can just put the square root over the whole thing, like so. There's an x and there's a 1 minus x. Plus c. I'm home. Okay. Now, like I said, some crazy restrictions on this, right? X is, well, it's positive. It's positive. Because I did this trick up here and assumed that sine inverse of sine theta was theta, I'm only between 0 and pi on 2. So it happens that this integral only works for, well, it only exists for a very, very small area, right? But sure enough, if you differentiate it back, you'll get the square root of x on 1 minus x eventually. Okay?